There we go. Okay, everybody ready? We good? So here are the hard software problems I'm going to talk about. Infinite loops, memory leaks, and memory errors. All of you guys have have written programs that have had these problems. Researchers have devoted decades of research to trying to solve these problems. I'm going to tell you how to solve all of them here today, and that's just the first half of the talk. Okay, so let's jump right in. What's an infinite loop? It's when the program runs forever and your program becomes unresponsive. It doesn't give you the service that you need. So what do? We built a system called Bolt. You run your program. The program becomes unresponsive. You launch it. It attaches to the program, identifies a loop, takes snapshots. The two snaps at the top are the same. It's an infinite loop. You just jump to the instruction afterwards and return from the function continuing the loop. Okay? You never have to have an infinite loop if you don't want one. So we built this great system over this. You can see the little dashboard here. It's got all your programs. If you suspect the program is doing something that's in an infinite loop and you don't like it, you can say, hey, I want to break out of the loop. I want to jump back out, and you can just continue the execution. Now, does this sound like a simple idea to you guys? Sure, it's relatively simple, right? But implementing this idea on stripped x86 binaries is anything but simple, which is why we have a great group that did it. We used all these tools, and now we've got an implementation we can play with. Now, who thinks this is going to work every single last time? Who thinks it'll never work? Oh my goodness. Okay. But what I think everybody realizes here is that this is an empirical question. So the way you investigate an empirical question is you get a bunch of applications and you try it. We got 13 infinite loops, 2 long loops. We thought they were infinite, but later on we realized they were long loops. They were just counting some counter up until it expired. Okay, but for you, the observable difference is it's just an infinite loop. And what happened? First question. Can Bolt detect the infinite loops? For 11 of the 13 of them, it can in fact detect them. This is an important thing because you want to be able to get out of a loop, and to get out of a loop, you've got to detect it before you get out. The next question, can it produce a safe terminating execution? In other words, when you jump out of the middle of the loop, maybe there's some invariant that you're not preserving. This turns out not to be the case. You can always terminate the execution, it's always safe. Now the question becomes, does it produce the same output? So what we did as the manually corrected version, so what we did was we looked through all of the revisions and found the the version where they actually corrected the infinite loop. And we said, will you get the same result with Bolt as with the correction? And a remarkable number of times the answer is yes. The pattern here is that if you don't get the same output, it's because the loop is processing part of the input, gets stuck halfway through, and you only get part of the output. Okay? Not a bad outcome if your alternative is to sit there and watch the program do nothing forever. Okay? So the one exception here is the Java virtual machine. Virtual machines are very complicated things. Interpreters tend not to work very well with these techniques because you've got a level of indirection between the program and what you're actually doing. So if you hack and then the program is just a bunch of data sitting off on the side, and the interpreter's running around in a loop. So it doesn't tend to work as well. But all the rest of them works great. Let's take a real quick, first question. Why? Why do infinite loops happen to good people? Okay? Missing transitions. Okay? So what you should think about for a missing transition is, you read a piece of input, you have a big case statement that says if this, and this, and this, and this, and they missed one of the case statements, and it comes in and just doesn't read any input. Okay, so you never reach the input. Sometimes you have an incorrect exit condition, and you fail to exit the loop and it's done. So let's take a look at one of these infinite loops. So what's going on here is it's going through looking for triple quotes. Okay, and it should every time update the location where it's finding the triple quote once it's found it, but it always goes back to the beginning because it puts string there instead of s. You guys can see how this could be a very easy error to make, right? Now the interesting thing about this is also it's a very easy error to miss during testing because you've got to have 2 triple quotes before you can actually detect the bug. This illustrates why you find these errors slipping through testing. There's all these crazy corner cases. Okay, so for some reason my laptop is going ahead of me. I don't know why, but we'll find out what happens when we deal with it, okay? All right, so 1 up, 1 down. Okay, next up. Yeah.
How can you detect this infinite loop if it doesn't have the exact same properties?
If it doesn't have the exact same state?
Yeah, because you can have something that just oscillates like that and never reaches the border. You have
Oh, so what we do is we keep this big buffer of previously observed states, and if we match any of them, then we'll see the loop. But you're right, okay? So but if you have an infinite loop where you're continually changing the state forever, which is harder than you think because you've got to be allocating memory to do it, then we're not going to detect it. But if you look back and see that only, I think, the Java virtual machine one and indent do that. Okay, now Gawk and Poplar here, both of those are long loops where they're counting things and it'll take forever to reach there, but eventually the loop will terminate. We just get out of it. Okay? All right, so one up, one down, down memory leaks. Look at the middle of the slide here where you see the standard memory leak thing with this memory consumption. You guys all see this? Memory consumption is going up. Why do you have a memory leak? You have a memory leak because you allocate data and don't deallocate it. In languages with explicit malloc and free, it's because you don't free something. Most people think you can't have a memory leak in Java or any other collected language, but the fact of the matter is that you can, because all you have to do is keep a pointer around to some piece of data you're never going to use in the future, and voila, you get memory leaks galore. It's a huge problem in Java programs. All right, so I'm here. You never have to have a memory leak. It just doesn't have to happen. In fact, you never have to start a program and have any kind of uncertainty about how much memory you're going to need to execute the program. And let me tell you how you do that. So let's say you have a leak at this original code where you allocate a node. Everybody with me? Here's what you do. You say, I'm going to have a buffer. That buffer is going to hold all of the objects that are ever allocated in that node. And here it is. It's 3-bit. You get 3 objects. That's all you ever get. Okay, so when you allocate, you just go around. First one goes there, the next one goes there, the third one goes there. Where's the next one going to go? Back there at the beginning. Okay? And I think everybody will agree that once you do this, you will never have a memory leak. You will never have, that's right, you won't have memory, it just won't happen to you, right? Because you can statically bound the amount of memory your program takes. Okay, I tell this to people, and I can see it all in your heads. Okay? They say, you can't do this, you might overlay live data. Okay, that's what everybody's thinking, aren't you? All right, so let's pretend for a minute that we're not in a technical conference. Let's pretend that we're in a humanities class. If we're in a humanities class, what are we going to do? We're going to do a close reading of the text. And we're going to unpack the text and find out what its true meaning is. So here's a text. The text says, you can't do this, you might overlay live data. If you do a close reading of this text, what you'll realize is that that's just false. We can absolutely do this. Okay? On the other hand, it is true that you might overlay live data. But again, the real question is, what happens? So, we went out and got a bunch of these programs and tried them. Squid, XMSB, FreeCiv. The funny thing about these apps is that they are all these network-facing applications, so they're vulnerable to these remote denial of service attacks. If you find an input that'll trigger a leak, you can repeatedly send that input to the program and take it down. Okay? So cyclic memory allocation eliminates all the memory leak. And it turns out that using this technique, we have some dynamic analysis that will go through and estimate the size of the buffer that you need. And if we get that, and we always get the size of the buffer right, we never have any overlaying of live data, and it's a pretty boring result because all it does is just eliminate the leak. Yeah?
So you can basically just measure how much it's actually going to be a leak in practice on by running it, and then you can set the size of the buffer ultimately free if it's something that's going to fit quite well. That's
right. So, what you do is, in effect, it's a dynamic sort of memory analysis where you go through and you find out what's the biggest number where you have to hold all the live data at that time. Looking forward into the future, because remember, it's a dynamic analysis, we know exactly what it's going to allocate because what's going to access it, so we look forward into the future and project back real quick. And we can always do it. So that was kind of boring. So we decided to half the number of buffers, half the size of the buffer, and see what happened. Okay, so here's what happens. What happens is we get graceful degradation, and let's understand why. So let's say we have a buffer that holds a binary tree. Okay, this is an example on RAS. And we overlay it, and we only give it, let's say, 5 instead of 6 elements. What happens is we're going to overlay, when we go around to allocate 4 again, it's going to write over 7. So now the first question is the data structure on your right consistent? The answer is no. Not consistent, right? It's supposed to be a tree, this is not a tree. Is it consistent enough to use? Sure, because if you run a binary tree lookup on this, it's going to run down the tree, it's going to follow a bunch of pointers, and it's going to find something or not. Is it going to get the right answer some of the time? Yes. Most of the time, probably. Does the program survive? You bet. And we replaced a fatality with a graceful degradation, which is a fabulous result. All right, so interesting patterns. So Squid has a leak in this SNMP module. Anybody know what SNMP module is? Anybody heard of SNMP? Can somebody tell me what the letters stand for? Say what?
Simple network boundary protocol.
Exactly. How old is it?
20, 30 years.
Yeah, it's unbelievably old. What's it doing in my web cache? Okay, there it is. Okay, this is a pattern that you see a lot of the time, right? Software never goes away, it just accretes and accretes and accretes and accretes and accretes. But the fabulous thing about this SNMP module is it's like your appendix. It's there, you don't notice it. Most people think you don't need it, but it's a part of your attack surface. And what these techniques let you do is close that part of your attack surface. Okay, now FreeSID, the leaks in the AI player's data structure. Okay, now, so we tried this, we overlaid it, we gave it less memory. AI player, as far as we can tell, plays differently, doesn't play any worse. You know, why do you need this data, right? So it's got the flexible, but so the data here, there's pieces of data in your program that are very flexible, where all you need is some bits. And you know, if you prevent the program from doing too many bad things, those bits will work just fine, even if it's not exactly what's going on. Okay? So as you expect, yeah, we got a question? Sure.
Sorry, did you modify all the object allocation, or did you like pick specific ones?
We picked the ones where we found memory leaks.
Oh.
Yeah. I think you'd have a tougher time if you tried to do everything. Right? But you know, on the other hand, the mainline functionality of the program often tends to be pretty correct. And what we're trying to do here is close off all the rough edges. But yeah, we didn't try that experiment. I'm pretty sure it wouldn't work. Unless, actually it might. Great question. Yeah. Paper at next year's conference, right? All right, so 2 up, 2 down. Memory errors. You know, what's a memory error? So everybody's written a C program. Here it is, you got this linear address space, you throw objects into the address space. They're not really objects, they're blocks of memory, because in C you don't have objects, you can just have blocks of memory. Great thing about C is you can have a pointer. You point that, and you point that pointer into the block of memory. You can access that block of memory using the pointer. You can jump around the block of memory using the pointer. You can jump out of the block of memory using the pointer. What happens when you do? It's undefined, but your program will definitely do something. Okay? So you get a bounds violation. It's data corruption, segmentation violation, security vulnerabilities. People have been working on this problem ever since, what, the 60s, 50s? Well, congratulations. It's now a solved problem. Okay, so people have known about this for decades, and what they do, this is not the solution. The solution, so what they did is they built these compilers that track the base allocated block. And every time you go outside the block, you check if there's no illegal access. And if so, what do? Well, I mean, you stop the program, right? It's clearly unsafe to continue. If it's accessing this memory randomly, you know, you don't do this, right? We have a different philosophy. Because the programs, once the program stops, you can't use it anymore. Our philosophy is we're going to just discard the write and keep going. This is an easy thing to do because when you're writing something, you're just throwing it away. It's like, you know, tossing something over your shoulder. The question becomes, what do you do when you have a read? Okay, why is the program, to unlock the answer to this question, you have to ask yourself the following question, the easier question. Why is the program reading memory? The program is reading memory because it wants a value. Okay? How hard is it to give the program a value? It's not that hard at all. There's 2 to the 32nd or even 2 to the 64th of them. You can choose any one. Okay? You just make it up, give it back, and keep going. Now, it isn't really that simple, because it turns out that some sequences of values that you hand back are better than others. In particular, this is a pretty good sequence of values. See, it goes 0, 1, 2, 0, 1, 3, 0, 1, 4, 0, 1, 5. Why is this a good sequence of values? Well, if you go off and look at the computer architecture literature. These guys do something called value prediction, where they try to predict what the value is going to be so they can make their branch predictors and their data predictors work a lot better. And you'll find that almost all of the values that your program accesses, reads, are either 0 or 1. So if you have back a sequence with a lot of zeros and ones in it, chances are you're going to get the right value anyway. Now there's some there's some programs that are finicky. They want a specific value. So what you do is you got to cycle through all the values until you give the program the value at once, and then it's happy and continues on. Okay? Now we call this, as I said, failure-oblivious computing, because what this does is it makes the program oblivious to its failure to access memory correctly. Okay, now you've seen, okay, I can go through all these, but everybody realizes that only wonderful things happen. Okay? But, as always, what about errors in continued execution? Well, let's see one. So, anybody heard of this Pine mail program? Yeah, we've used Pine before. Turns out that certain versions of Pine have this vulnerability where you can send somebody a message. It's got the from field that has, a carefully crafted address in it. You put it in the mail folder, and Pine reads the message. When you start up Pine, it's going to read your mail folder. Turns out that if you put this message in your mail folder, you can exploit Pine even before the user interface comes up. Type PINE, return, you're exploited, you don't get to read any of your mail unless it's a user-friendly exploit that lets you read the mail while it's busy at the building system. Okay? So, what happens, so why is this going on? It turns out that there's this unfortunate quoting rule where you replace backslash with double backslash and quote with backslash quote so the from field can double in size. But the buffer that holds the translated from field isn't twice the size, so you can see what happens. It's going to overwrite it like that. Okay. What happens with failure-oblivious computing? You're just going to discard all of the writes. So the from field is effectively truncated. So now you can see why you have to give it a pretty good sequence of values, because when you truncate that from field, eventually you may have code that's going to treat it as an ill-terminated string. And it's going to run off the end of the buffer and it wants to see a 0 there. So if you give it a 0 pretty quickly, it's happy and it goes on its way. What are going to be the consequences of this? The consequences, one potential consequence might be that you're going to see the wrong from field, correct? Well, it turns out that in fact you don't see the wrong from field, because it uses that from field in this user interface right here, where it's truncated at 18 characters in the user interface. And the buffer may not be big enough to hold the full from field, but it's definitely bigger than 18 characters. So once you apply this technique to this bug, the program is indistinguishable from the fixed program. Okay, and then again, this is another common pattern you see in these programs. There's a lot going on inside the program that doesn't actually surface in the user interface. So if you can do things to keep the program going, a lot of times you can get lucky and make it survive. All right. So here's another one. Apache has this redirect match command. What you do is you use it to translate things like you read GIF into http://images.com, you read JPEG. Okay, it's a way of translating URLs again. And what you can do, and this pattern should be familiar with many of you, is you can capture the regular expression on one side and then reference it in the right-hand side. Turns out that they only have room to store 10 matches because they're storing the start and the end offset inside this array that has 10 elements. So now, of course, once you know this, if you give it a command like that, that has 11 instead of 10 elements, it's going to write the capture beyond the array bounds. Okay, problematic bug. Okay, with failure-oblivious computing, you can just discard it. Now, the obvious question here is, well, if you discard it, you cannot possibly preserve the behavior of the system, right? Because you can't access that 11th captured string. So there's going to be a problem. But let's look at this a little bit. Turns out that the only names you have are $0 through $9. So if you type in $11, you don't get K here because that's the 11th thing. Instead, you get B1. So again, the behavior of the program is completely indistinguishable from the behavior of the fixed program where they just discarded everything beyond the 10. Because nobody wants to use 10 anymore, more than 10 anymore. Okay, so what are the results? I can blast through this pretty quickly. What we've got here is You see the column here? It's got 3 different columns in it. There's the SC column is the standard compilation column. That's the compilation with the C compiler. We type GCC, this is what you get. Bounds check compilation, this is with the modified GCC that has the bounds in it. Here, if you exceed the bounds, you bail out and the program stops. FO is failure-oblivious. You keep going using the mechanisms I just described. First question, I'm going to ask 3 questions. First question, is the program secure? The answer with standard compilation is none of these programs are secure. They've all got a bug being triggered. With bounds check and FO, they're all secure. Okay, great. I got a secure program. I want more than that. Does it initialize? Turns out that sendmail doesn't initialize with bounds check computation because there's a problem in there. There's a memory error, just an initialization code. Okay, now Pine and Mutt, it maybe it initializes because it depends on the configuration file you give it. The failure-oblivious computing course everything's great. Last question is, does it continue correctly? Okay, now this is a slightly different concept here. Turns out that, let's take Pine for example. What Pine does is it processes a sequence of mail messages. If you get one mail, the question here is if you get a mail message that attacks that vulnerability, does it correctly process the subsequent mail messages? Okay. Similarly for sendmail, and Apache does it process subsequent things correctly. It turns out with failure-oblivious computing, it always continues correctly. The way you should think about this is the program takes a hit, then recovers and keeps going. Okay? Whereas with standard compilation, bounds check compilation, it's all down the drain. Now the exception here is Apache. Apache can continue correctly with all of them. The reason is it has this nice mechanism where it has a regenerating set of threads, and it processes each request in a separate thread. So if a thread dies, Apache itself doesn't die. That's a very nice robustness mechanism if you can keep the error contained in the thread. And what we're doing here with this technique is very similar to that philosophically and conceptually. We're confining the bug to the processing of that individual message, even though it's a sequential program with one thread. Okay? All right, what's the pattern? I've been through this before. Pine to server processes a sequence of messages, so it's not really an input file, it's a sequence of messages. When you go off and look at a lot of applications, you'll see they all have this structure. So now what happens with standard semantics, if you get a message that triggers a fatal error, it turns out that your application is down the drain and you're screwed. With failure-oblivious computing, you may get an error, but the error is localized because you don't do any out-of-bounds writes. This is critical to making this technique work. And then it survives to go on and process the next messages. Okay, and the pattern generalizes. A way I like to think about this conceptually is if you're writing a server, in effect the server is sitting there processing a sequence of packets that's being sent to it. Okay, and what most applications do is even if they take a continuous stream, even if they read an input file, the very first thing they do is they chop that input up into conceptual packets and process them one at a time. Okay, and this is a pattern that once you recognize it, you can exploit it, which we've done. So Wireshark goes like that, it works for general applications. So here we are, 3 up, 3 down. All right. Okay, so where are we going from here? Well, let's talk about some empirical facts. Most applications are servers. They support these robustness mechanisms. It turns out that once you recognize this pattern, you have this thing called filtered iterators, which we published here last year, where you use the program itself to recognize bad inputs. So the program itself is ineffective. So that was a piece of research I liked a lot because it was the end of a long arc that started with some very empirical techniques and then reified those techniques into a principled programming mechanism that you could use. I like doing this. I like going off, trying crazy things, see when they work, understand why they work, and building systems that go in and make that structure explicit so you can use them. Okay? Potential implications, better systems within practical reach, more secure, more robust. I'd like to talk a little bit about the cognitive capacity here. Everybody knows that when you're building a software system, the limiting factor is your cognitive capacity. Anything you can do, that's a limiting factor. Anything you can do where you have to spend less of your cognitive capacity to build a system is going to enable you to build either the system cheaper or build a more heavily functional system. Okay, what do you think everybody's going to choose to do? More functionality, right? There's no such thing as too much functionality. Everybody wants more functionality in their systems today. So every time, that's why they hire more people, is because they're trying to get more cognitive capacity. All right. So key insights, applications are inherently flexible and resilient. Simple mechanisms can expose this flexibility and resilience. These mechanisms can improve software and open up new points. Why do you think people, actually I'm not going to talk about that now, I'll talk about it from the slides. Okay,
So
yeah.
I think, like I said, applications are inherently flexible and resilient. Do you think that's the particular kinds of applications that you've looked at, as in, for example, servers and like web-based applications?
Yeah.
Versus site implementation or different kind of program?
Well, I can only answer the question for the programs we've tried. We did a whole bunch of research on proximate computing, where we went in and started dropping loop iterations to make the program run faster. And we did that to a lot of scientific computing applications, a lot of interactive applications, some image processing applications. I mean, my conclusion after all this is, people think of software is this big, hard, rigid system. It's not. It's like this big piece of jello. You can twist it, you can morph it, you can squeeze it, and as long as you're not obsessively trying to crash it when the first thing goes wrong, they bounce back and they keep going. They do really well. I mean, once you start pushing these techniques onto a system, trying to crash it, which is what some of my students did, it changes the way you think about software. All right? But there is one thing. We first started doing this on small kernels, sorting things like this. And if you do anything bad to those things, they'll just fall over and die. Okay? The bigger the program, the better it works. Okay? And there's a result that I've tried to do for decades and never been able to get the people together. If you guys could do that, it'd be great. The better the software is written, the worse it behaves in these things, right? If you breathe at the very heavily optimized, very well written inner core of some application, and do the least little thing to it, the thing will fall over and die. Okay? In fact, if you look at this application, which is one of my favorite applications, Midnight. This is Midnight Commander. Okay? The reason it's called Midnight Commander is it was a substitute for Norton Commander written in some guy's spare time at midnight. And if you look at the code, it is disgusting. It is unbelievably bad. In fact, if you look at the stuff, and it's hard to figure out even what the right answer is for this code a lot of the time. On the other hand, you cannot make this code die. It just keeps coming back. Right? You knock it down, it's back. Yeah.
So our advice to undergrads?
Right? The worst. I don't know.
Just following up on your train of thought.
No, I mean, it's a great question, right? It's one of the most intriguing things I've found about this, right? Because the better you're think about it, right? What does good code do? Good code says, I know exactly what's going to happen. I'm going to do only the minimum amount required, and everything's going to work out okay. Bad code is, well, I don't really know what's going on here. I'm going to write a bunch of stuff out of there, and I hope it's all working out. And it turns out it's more robust. It's one of the most counterintuitive results, and I've never been able to. Here's what you'd like to do. What you'd like to do is go out, try these mechanisms where you perturb the code somewhere, add off by one errors, remove loop iterations, cause all these bugs, and correlate the resilience you get against some metric that measures the quality of the code. And I bet they'd be inversely correlated. Say what? Yeah, that kind of stuff. I mean, I'm not sure how accurate they are, so you can get a bad result, but I don't know. But yeah, we got another question.
So a related, or maybe not quite directly related method for perturbing code a little bit and see what is going to happen is mutation testing.
Yeah, exactly.
In your experience, how do they connect?
So
do they?
So people do mutation testing from the wrong perspective, in my view, right?
Because the goal is to catch the mutant, not to allow the mutant to survive.
Exactly, right? So from this perspective, what you want to know is what percentage of the mutants actually survive and do well. And as I said, the hypothesis here is that it's inversely correlated with the quality of the code. So you got to find. So it would be a great experiment to run. And
so you're saying if it's hard to find the mutants by making one mutation, then what we're talking about here is sort of built-in redundancy essentially in the program.
Exactly.
It's more redundancy.
Yeah. And another way of looking at it is, it's so bad, how worse can it get? Right? Because, and think about it, right? If you've got this pristine white cloth and you drop one drop of dirt on it, you can see it immediately. If you've got this disgusting piece of cloth full of dirt, you drop one piece of dirt, there's no difference. So maybe our sense of aesthetics for code is just all wrong. I don't know. All right, so anyway, I want to get out of this and go on to the second half of the talk. Okay, so here's a picture that I'd like to talk about this. Here's all programs. And the green programs are the correct programs. The red programs are the programs you get from the developer. Notice they're not the same program. Okay, the programs you get from the developer are always incorrect. What these techniques do is they put this nice little bubble around it and make them the same under acceptability. Okay, which is really nice. Now, I've talked about these techniques for a long time. And you'd think, and it's hard to do better than this in a research program. Right? This is a great result. But I meet resistance. People say, you know, you should get the program right. You know, I want to know if there's a bug. You know, this, that, and the other thing. And I think part of that is just the perspective of people who I'm talking to about, people in the research community. How many of you guys actually write code or have written code? Okay. When you write code or have written code and you have a bug, you want to know about it, right? You don't want the program to just keep going and doing something crazy. So your perspective is, I've got the program there, and there's somebody there who knows how to fix it and can fix it quickly. That's not the situation most software is in when it's out in the world. Okay? So on the other hand, there's this technique, there's this philosophical phenomenon called the bystander effect. Turns out that, let's say you have somebody at the end of, an inspector at the end of an assembly line. If you have 2 inspectors, they catch fewer defects than 1 inspector does. Okay, and the reason is each inspector is relying on the other inspector to fix it, to find it. Whereas 1 inspector knows if they miss it, it's going to be him or her, that person only. If you introduce these techniques into the software development process, all of a sudden you've introduced a bystander. It's no longer your developer's responsibility to make the program correct. It's these techniques' responsibility. So my hypothesis is that you get much worse code. So how do you use these techniques? What you have to do is you can't tell your developers you're going to do it. They have to be ignorant. They have to believe that their code is going to be the code that runs. And only then, into deployment, you put this into effect. All right, so the people don't want this. Actually, people want the effect, but they don't like the picture. What picture do they want? They want this picture. They want only correct programs. Okay? Now, this seems unreasonable, right? The world's not a perfect place. Everybody knows you got to make compromises. But it turns out that there's a way you can get this to get close to it. Okay? That's what everybody here knows, and everybody here does research in. That way, it's called domain-specific languages. Actually, what domain-specific languages do is they throw away all these buggy computations. Okay? Well, life is wonderful. If you go and talk to, okay, so for how long have people been doing domain-specific languages? Yeah, whatever. 1957? Which domain-specific language are you thinking about? Not Fortran? Yeah, there you go. Right? People have been doing this forever. And in fact, if you go to Google Scholar and type in domain-specific language, you can pull all these papers off like the first or second page. And they do all kinds of stuff. My favorite here is a domain-specific language for models of landscape dynamics. I don't know what that landscape dynamics are, but it sounds like it's pretty interesting. And the great thing about this field, is you can do it in any context. If fashion changes, you just do a different domain-specific language. And you can see this by the 2 at the bottom, right? What's the most fashionable thing in computer science today? Machine learning and deep neural networks. Well, you can do domain-specific language research in that. What happens if all of a sudden, as inevitably will happen, machine learning and deep neural networks go out of fashion? Something else comes in, and all you do is build a new domain-specific language. Life is great. It's a strategy for, and yeah, you never have to stop being a researcher. You know, just follow the fashion. And it's active here. Here's a bunch of, I go to the SLE website, 2018, and really briefly scan all the papers, and at least these papers are all dealing with domain-specific language. Okay? And if your paper isn't here, I apologize. You should have put domain-specific language in your title. Okay, so now I want to take a step back in time to 1984. In 1984, I was a software developer. I hadn't gone back to graduate school yet. I was working in a startup, and then I worked in another startup. We always built our systems by building a domain-specific language, generating code for it, putting it all together. And it was a fabulous way to build systems. Systems got built really quickly. They were super flexible. Life was great. So then I went back to graduate school, and I kept watching the field over time. And I always wondered why domain-specific languages weren't used more than they were. You know, you'll see domain-specific languages around, but since it's such a fabulous way of developing systems, why aren't they used all over the place? Why do people still continue to develop their programs in these general-purpose languages? So then, a couple of years ago, I finally had an experience that gave me insight into why this is the case. Here's the experience. I was doing consulting for a law firm. The law firm said, hey, we've got this, our client has this software system, and you got to tell us if this software system infringes this patent we've got. I say, well, send the software system over, let me take a look at it. I unpack the file. Turns out there's 6 different versions of this software system. So I call the lawyer back and say, okay, you got 6 different versions here. The guy says, really? I didn't know that. I say, well, which version do you want me to analyze? The guy says, I guess all of them. So I got the opportunity to analyze 6 different versions of the same software system. Okay, doesn't sound like the most inspiring work, does it? Well, it turns out that I finally figured out why domain-specific languages aren't more popular than they are now. And here's why. Version 1. Turns out they had a domain-specific language. And you had the source code for that domain-specific language. You could see it was processing sequences of user actions. And you had the generated code, because you could see where the code was generated. And the system had all these mesh-generated patterns. Version 2, the source for the domain-specific language is gone. But all the generated code patterns were still there. And you could find places where people had copied and pasted them and changed the variables around because they needed to add additional functionality. Okay? In version 3, the pattern was still there, but the pattern starts to degrade, right? You know, they weren't doing exactly the same thing. You could see that people were just kind of playing around with it. Version 4, degraded further, but now there's a new pattern present, and it's all written in C. Okay, all these things are C. Version 5, you can see that they're trying to get rid of all the initial generated code from the domain-specific language. And in version 6, they finally got rid of it, and now the program is all written in C. Okay, question is, why did this happen? And here's why this happened. In version 1, who's building version 1? The ambitious, technically sophisticated people who are out there building the new product, saying, this is great, I want to do it. After version 1 is complete, deployed, and works, you're on to version 2. Where are these guys?
On to the next thing.
On to the next project. Can you just leave the software sitting there unmodified? No. You've got to hire somebody to come off and work with it. Who are you going to hire? C programmers off the street. The C programmers off the street resonate deeply with this domain-specific language. Turns out that they don't. They just say, what is this? All I want to do is write my code and go home. You don't? Okay? So they don't want to learn your language, and they refuse to cooperate with you if you try to make them. Because they can always find another job where they only have to program C and they don't have to learn some new language. That's why, or at least that's why I think why, these domain-specific languages aren't as popular in practice as they ought to be if the world was great. Yeah?
So if we have a DSL, you're telling us what we should do is generate completely obfuscated code, and then
well, what do you think would happen if we did that?
we might not start with version 1.
That's right. I mean, you know, what would happen is, you know, you'd have an engineering, there would be consequences. Okay, so, but let's think about a little, but okay, we'll see there's a way to make domain-specific languages actually worthwhile, but it's going to take a little while to get there. Here's how I'm going to get there. What's going on today in the world of software? Well, everybody is learning how to program. All of you are aware that computer science departments worldwide have huge numbers of undergraduates. It's going up and up and up and up. And it's not just computer science majors, it's everybody. Okay? And in fact, if you go to Stanford University a couple of years ago and look at the enrollment in their introductory computer science classes, count the number of people there, the number of people you get is larger than their incoming freshman class. Okay? Everybody is taking computer science. And what does that mean? It means that being able to write programs is now a basic literacy. It's just like reading, writing, and I guess doing arithmetic, although not everybody can do arithmetic really well, but still, it's part of that being basic literacy. So now we have all these people who know how to program. What are they learning? They're learning Python. Okay, so they can write these basic Python programs. What does this mean we have? Well, do we need Python programs? I guess. Do we need basic Python programs that these guys can write? No, we need programs that can execute all these complicated programming environments, right? The cloud, all this stuff. What's the defining feature of these complicated programming environments? They're difficult to write code for. They got ridiculous APIs. You cannot figure out exactly how to use them because you've got to sit there and type keywords into Google all day long and hope you find the API code sequence you need. Okay? So we've got a mismatch between these people. Now, how easy is it possible to use these environments? Sure, people use them every day. Are the people we're graduating able to use these environments immediately? Nah. In fact, if you look at it, you'll see that the general public, as you can see, is clueless about what's going on here, right? Stack Overflow. What does Kubernetes actually do? This poor person's gone off. Somebody told him, hey, this is a great system, you got to use it. We're using it at work, blah, 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 blah. He reads all the documentation, he still can't figure out what's going on. This is a common thing, right? You look over, here's another one, right? Now you've got Spark. Here you've got somebody who has years of experience in object-oriented code, knows how to write good code. All of a sudden, Spark comes along, what's he say? All the best practices tell me to write spaghetti code. Help, 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 help. Okay? And so what we've got is we've got this big gap between people who can write simple programs that run on their laptops and all the code that can run in these complicated environments. Here's the question. Can anybody write code with these environments? Well, sure, somebody can. And what I'm going to tell you about today is how to take that person, dump them into this program inference and regeneration system, so you take these simple programs and regenerate them onto the complicated platforms. Here's the key insight that makes this work. The code that's running on these platforms does not implement, typically, very sophisticated functionality. If you just want the core functionality, most people can write some simple text-based Python program that doesn't. All the complexity is knowing which APIs to use, how to deal with these funky things like replication, unreliability, all this stuff that complicates your life. So the idea here is we take this program that implements the raw functionality and we regenerate it to include all of these other things that we need to make it go well. So here is the basic picture. We take a program, we're going to interact with this program by like a black box, learn exactly what it does, so now we've captured the representation of what it does, and then we're going to regenerate and include all this stuff to use the APIs. Okay, we tell this to people, their first response is, you can't possibly do this. Here's why. Let's say I give you this program. You can't figure out what this program is going to do because you've got to try all the inputs. You have to exhaust the input space. Well, that's a problem. Are we going to try to do this? What happens when you are presented with an insoluble problem? You find a way around it. Okay? But then people say, wait, I was wrong. You can do it. Here's how you do it. You just record all the inputs and get back the outputs. But you don't want this either. All right, so how do you solve this? What we need is a model of computation. We want to rule out these computations that we can't infer. We want to rule out these degenerate solutions. It also lets us work with imperfect programs because if the program contains the bugs, chances are if we use this black box learning approach, we're going to miss most of the bugs because most people can get the common case correct. And if we only care about the functionality within this model of computation, we can learn it. All right, so what I'm going to do next is tell you how we go through this and do it for an example. Everybody ready for it? Okay, there are these CRUD programs. They are create, read, update, delete. What they do is they have a bunch of maps and they just insert and read stuff out of the maps. Okay? Basic abstraction, the application implements a collection of maps. Each map stores these key value mappings. The operations do various things on them. It's a very common pattern and a very useful pattern, and a pattern that can be somewhat difficult to implement on a gigantic distributed computing platform. Okay? So here's our example. We're going to do a student registration example. We have a bunch of store operations on the left, retrieve operations on the right, and some unknown number of maps in the middle. The goal is to figure out what's going on. So starting point, we're going to assume here that we're working with a simple text representation we can use and practice anything we can interact with successfully. What do we infer? The number of maps, how the operation store values into the maps, and how operations retrieve values. How are we going to do this? We're going to use active learning. Okay? So Active learning, what does active learning do? What? Okay. You got to see. Machine learning is now fashionable. You have to be able to say things like active learning. You know, what active learning does is it says, I want to know what something is doing. It's an active thing, so I can interact with it. I'm going to choose my inputs, observe the outputs, and develop a model of what's going on inside. So that's what we're going to do with this program. So let's think about how we would develop a model of this program only by interacting with it through its interface. So we have to tell our program what the interface is. So the interface here is we've got enroll, rename, add, and drop operations, and we have ID, name, and classes operations that retrieve information out of these maps. Okay? So what do? We say we have our algorithm. First thing we do, we start with the initial empty maps, and we type. We say, well, I'm going to enroll the student A with ID 7 in year 2018. Okay, all the values have to be distinct. You'll see why. So then I hit it with the. Then I try to retrieve A and I get back 7 out. What do I now know? I now know that there's a map inside there, somewhere. Don't know where it is, don't know which one it is, but I know the map. Okay? I know that enroll is going to insert 7 into that map under A. And I know that ID is going to access that same map, and when I give it A, it's going to pull 7 back out. Okay? So all of a sudden, I've got a store-retrieve pair that captures that potential interaction. Okay, now, I do it again. Now I type ID 7, and nothing comes out. So now I don't know there's a map there, but I do know that this thing is unrelated. Okay? So now I just keep doing this, and now I found another one. Okay? If I type name 7, I get A back out. So now I know there's a different map inside there. I've got 2 different maps. And I keep doing this, and eventually, by probing these things, by inserting things, and retrieving them, I developed this idea that there are 4 store-retrieve pairs. And if I can build a system that generates these store-retrieve pairs, I've captured the behavior of the system, and all of a sudden I can use whatever I want. I don't have to use maps in the program. I can throw this original program away and do whatever I want. Now, I'm almost there, except, do I have 4 maps? Well, I have at most 4 maps. My last problem is I have to decide whether some of these maps are the same map. And let me tell you how I do that. So it turns out that these 2 operations, enroll and rename, all manipulate the same map. How do I figure this out? I run an enroll operation, and run a rename operation, and then you see how I have the same name operation on the right? See how it gets the same answer whether I put enroll or rename there? Well, the name operation always accesses the same map. Therefore, I know that the enroll and the rename operation also access the same map. So now I know I've got 3 maps, not 4. I've discovered all the information I need to completely characterize this program's behavior. All right, so now what I'm going to do is I'm going to capture this model of computation in domain-specific language. Okay? I'm going to have the domain-specific language. I just tell what the maps are. I tell what the store operations are and how they manipulate the maps. I tell what the retrieve operations are and how they manipulate the maps. This is an inferable language. Okay? If this is a restricted model computation, I can use active learning to uncover any program, the semantics of any program that's going to conform to this model of computation. Okay? And now think about what I know. Let's say I want to implement all these maps using Redis. Does the person who wrote the small Python program that uses Python hash tables to implement these maps need to know how to use Redis to get a version of the program that uses Redis? The answer is not with my regenerator. Because my regenerator is going to encapsulate all the information about how you need to use Redis. Okay, it's going to generate all the little boilerplate you need. It's going to generate all the configuration code. It's going to go out into your computing infrastructure and configure everything, and all of a sudden, bingo, you're using this complicated system with only Python expertise. Or, let's say you don't know Python. Can you write it in Perl? Sure, right? I don't care. Can you write it in Java? Yeah. Can you write it in assembly language? Sure. Doesn't matter. All I care about is the interface. All right. What do we know and what not? So this is what we don't want to know. We don't want to know the internal structure of the program. We don't want to care about it. We don't want to know the language. We don't know if there's any bugs. The packages, all this is irrelevant to us. Don't know, don't care. The only thing we need to know is the maps and the actions that store the retrieve actions perform. All right, now we can augment all kinds of stuff, right? safety and security checks, fault tolerance, you name it, we can regenerate it, life's going to work great. All right, now, I want to talk about one thing. I've talked here about black box inference. Turns out that if you do black box inference, you're limited because you have somewhat of a limited visibility of what the program is doing. It's difficult and it can be difficult to build a model. So we've moved on. We're now doing this gray box inference thing where we have a bunch of major components inside the program, and you can observe not just the inputs and the outputs, but also the traffic along the component interfaces. So we've got, for example, something that will infer the behavior of a web interface to a database. A lot of applications out there in the world have a relational database and a web program sitting in front of it, and you want to interact with it, and you interact with the web program, and it goes back into the database. What we can do is track both the database traffic and the web traffic and come up with a more sophisticated inference algorithm that will tell us exactly what the behavior of that individual web thing is. And the great thing about that is we can then regenerate it with an emphasis on putting all safety and security and privacy checks in that people miss so often. So that's another way of making the system better. All right, so I want to get out of this talk. Software is important. We need better software. 2 ways to get it: survival and resilience techniques, program inference and regeneration. I didn't do all this research myself. I had fabulous collaborators who made it all happen. I'd like to acknowledge them. Here are the conclusions. On their contributions, I'll take any further questions that we've got.
Okay, questions?
Yes.
So regarding the last part of your talk, all these probing queries,
Yeah.
how is it different from basically writing an algebraic specification and then deriving a model from the specification?
Oh, it's very different because you're writing a program that interacts with the running program. Okay, so you have the running program there, and you're just building a model. So write an algebraic, first of all, people can't write algebraic specifications. It's almost impossible.
Well, but all these queries, like rename of such and such, uses such and such. I mean, you could observe all these results, and that is your specification.
Oh yeah, absolutely. Okay, so if you want to have an algebra, if the way you like to think, so that's a great question because what we're doing here is we're building a representation of the program in a way that we can manipulate effectively. We don't have a strong ideological position about what that representation is going to be. Okay, we like to think of it as a domain-specific language. But if you have an algebraic specification, that's what you want to work with, and that's your domain-specific language. Absolutely great because that's a representation you can manipulate and generate out. Okay, but again, what that points out is we're looking for a different kind of domain-specific language here. We're not looking for a domain-specific language that is easy for people to use. We're looking for a domain-specific language that is easy for programs to manipulate and work with.
Well, actually, I had a question at the end there. So I was interested, you're going to split them up into large components and look at the interfaces between the components. So presumably one of the reasons why that works really well is because large components tend to have well-defined interfaces that are not always that big, right?
Interposable interfaces, yes.
Yeah, so if you look at a database with SQL, you need to
Yes,
there, I guess.
exactly right, yes.
And then web, it's HTTP, for example.
Exactly.
Okay.
Yeah.
So does that mean that there is a natural decomposition that works well?
The answer, we don't know, right? There are certain natural decompositions that we can see right now that work well. So, for example, there's a lot of programs use databases. That's an obvious place to go and start interposing your code. Having said that, in projects I didn't talk about today, my research group has developed a lot of very powerful techniques for instrumenting and observing even assembly language code. So we've got another project that's just starting right now where we're doing white box, completely white box exploration of the program, where we can get symbolic expressions that completely capture the derivation of values in the program, starting from the input bytes and constants within the program. That's a very powerful technique or can be, because then you know exactly what the computation is doing, even down at the byte level, and you can regenerate computations that way. So I think there's an enormous scope for doing everything all the way from black box to pure white box approaches, and the one you're going to use is going to depend on what's appropriate for the situation. And I think the longer term vision here is treating the entire digital computing infrastructure as nature. Right? The physicists go out, okay, so think about this. What do physicists do? They want to understand nature. They treat nature sort of as a black box. They do all this stuff. They do active learning on nature. Okay? Right now, the global computing infrastructure is basically nature. Why shouldn't we do the same kind of thing on nature? Why shouldn't we go out and systematically design experiments and techniques that will allow us to come through and observe what's going on and build models?
Feels like we're taking a kind of assumption at that point, though, which is, nature is kind of chaotic in its existence, I guess,
Yep.
and it's not designed. Well, it's not designed in a sense that we would imagine. Is that how you're thinking we should be looking at software?
Yeah, because I think it's a pretty. With every line of code that you write, software becomes ever more chaotic, ever less predictable, and ever less well understood by the people in the world. So, nobody understands even a fraction of what a major website such as Amazon does. And when you start putting everything together with all the embedded devices, all the smart homes, the whole world going on, it's a very productive place for scientific exploration. I'm sure there's all kinds of interesting phenomena we can discover.
So you're a bit of a software cynic then, really, is that fair?
No, I'm so optimistic, right?
Okay.
I mean, I'm just saying, life is one. Okay, imagine how boring life would be if you designed everything and understood everything, you knew exactly what was going to happen.
Cynical about the structure, but optimistic about the opportunity.
Yeah, emergent complexity is fascinating, and the opportunities are in fact boundless.
Any more questions?
I'm sure you've heard this comment a lot, especially about the first part we talked about,
Yeah.
failure-oblivious computing, I guess.
Sure.
It kind of makes me not want to be a computer scientist anymore. I mean, just hear me out, right? On the one hand, it's like really, it's fascinating, right? It's amazing, and it works. And like, well, it works, this is great. On the other hand, I'm sure a lot of people find it also deeply disturbing in the sense of like, what do you mean you just like throw stuff away? You can ignore this bits of data. And you wanted to write, it doesn't matter, right?
Yeah, exactly.
Can you say more about, why am I, on the one hand, I certainly understand your message and that seems to work. But, initially I was thinking, gee, all right, this is maybe fine for Pine or some web thing, but do I want this in my pacemaker? Well, maybe, it won't crash, so maybe it's good there, but going on an airplane,
So,
how do you, maybe the real question is, what about safety critical systems?
So here's what, so I've gotten that question before, but I think it's a great question. I'm going to answer it in two ways. Okay, I'll first answer the last question you asked, which was, do you want this in safety critical systems? And the answer is that this is useful in different kinds of systems depending on their use case. Okay, so if you're in a use case where you can afford to stop the system, refuse to give service, go in and develop it, then I think these techniques are less useful because, and in the classic case there is debugging. I think when you're debugging, you want to find as many errors as soon as you can. Okay? Now, the most important use case is where if the thing stops running, you've got a guaranteed disaster. Okay? What are examples of this? Flight control software. Okay? You ever heard of the Ariane 5? Okay?
Everyone's at the end.
Right. Okay. So, I mean, everybody makes their own point with the Ariane 5. I'll make my point with the Ariane 5. Okay? The reason the Ariane 5 didn't crash, the reason the Ariane 5 didn't fly was because of paranoid software engineering. Okay? They shut down the control system on that rocket for a value that, because of an overflow of value that was not used. If they had just ignored that overflow and kept going, which they should have done because if you kill the software, the rocket's dead, the thing would have gone fine. So you need these techniques the most when you can afford to have a crash or a failure the least. And that's in safety critical systems, systems that have to keep running, otherwise you have a financial disaster. Okay? Systems that are old and nobody knows how to deal with. That's what these things do. Okay? So now the question, I want to answer your question though. Why are people so disturbed by this? Okay? And I think people are disturbed by this because if they believe that software really has this property, you cannot write programs. Think about it. What do you have to do to write a program? You have to sit there and you have to believe deeply that what you're doing is important. People are unable to convince themselves to do stuff that they think is unimportant. And people, you have to enjoy what you're doing. You have to enjoy doing all these precise systems and getting them perfect. This is a key thing that a lot of programmers have. And it's not a bad thing. It's just a delusional thing. Okay? I mean, sometimes you have to believe something is not true to be effective. And this is an example.
I think Eric and I and a lot of other people would feel a lot better if at the same time that you overrode a malfunction of the system,
Yes.
you would log it and inform the creator of the software that there's a problem and that you better go about and fix it so it doesn't happen again.
Yes.
And the other thing is, maybe in flight control, this may not be possible, but you could also, and you probably will, inform the user at the very moment that it overwrites values or does something, that it's doing just this, and whether the user wants to continue with the computation or just exit.
Just exit. Yeah, so you can do that. Let me answer those two questions. First, actually we do generate logs. Okay? And we find that nobody ever looks at the log. In fact, what I suggest you do, those of you who have Linux machines, other Unix machines, the operating system is logging all kinds of stuff. I suggest, okay, how many of you have actually looked at that log? Okay, and what did you see in that log?
A lot of stuff.
And did you worry about that stuff too much?
But I was trying to look for something specific, I guess. But
Yeah, but otherwise you go, whatever, the machine's doing something crazy I don't know about that, right? So that's, so that, I mean, I'm not saying it's a bad idea, we'll absolutely log it, but in social systems, it's very difficult to get people to pay attention to these kind of things when everything else looks like it's going fine. Which could be a bad thing or a good thing, but it's just a thing. So we absolutely provide that functionality. We're happy to do it. You want to look at the log? Absolutely. Now, as to whether you should let the user do it or not, that I think is a fine question. It's easy to provide that functionality. We can. The problem, though, there's two problems. One is, in some of these applications, there's thousands or hundreds of thousands of events happening. And so it's hard for people to say yes 1,000 or 100,000 times. The other thing is that pretty soon people will become used to seeing these things. I mean, how many of you guys read the fine print on all the end-user license agreements you present with on a daily basis? Not very many people. They say, whatever, click, 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 click.
So I started reading the once I can opt out. And that's one thing that actually
There you
changed,
go.
right?
Yes, yeah, yeah.
Now
Same
opt
change.
out of all these things and then you start reading them.
Yeah, exactly. So, yeah, I don't know. I mean, I can't predict exactly the social consequences of this. Like, all I can do is make analogies to the existing systems. The bottom line is, yeah, we generate this. It's not bad for us to support this. I'm happy to do it.
To do. So
Yeah.
I was just wondering whether you were actually thinking about looking at this kind of consensual.
Yes. So the answer is yes, we thought about it. Yes, we support it, but we're not motivated to do the research about what the, we got to talk to some social
Too
scientists.
simple. It's too simple.
No, I wouldn't say it's simple. It's actually quite complicated to figure out how people are going to interact with these technical systems. It's just not within our area of expertise or interest. But we are talking to social scientists for other projects now. Maybe we'll get some sense there.
Cool. Any more questions?
Yeah, so I was really intrigued by this point about the worse code doing better when patched and fixed up in this way. I'm curious if you think there are sort of lessons we can draw from this for software engineering practice. Not to write worse code, but maybe to write bits of code that are much more tolerant of other bits of code being very bad or something of that sort.
Yeah, I thought about this. It would be really nice if we were able to write fault-tolerant, resilient code. Okay. The problem is that it's hard for people to do that. And the worst kind of bugs you find are the bugs that you don't think can happen. Because if you don't think the bug can ever happen, you're never going to write code that does anything for it. So it's hard to motivate yourself to do it. And for that reason, I think people find it very challenging to write resilient code. I think if you put people in a situation where they don't really know what's going on, then maybe they're better, but force them to write code, then maybe you get more resilient code because there are fewer assumptions they can rely on, and the code is going to have to handle more cases. I hate to say it, but I mean, maybe the best thing you can do is just try a range of programmers, see what code they write. And I would go out, if I was going to, I would love to do this project. I've tried to fire on it 3 or 4 times. I've never been able to get it to work because the students just basically say, I'm here to do computer science, not this other stuff. And, but this really is, I think, an important question. I think it would be a blockbuster result. Go out on GitHub, pull out all this code, start doing mutation testing on it, and correlate the mutation testing with all of these models of software quality. Okay? It's a well-defined experiment. I've laid it out. I've talked to people that are doing it. I've even fired on it. If you want to do it, talk to me. I'd love to be part of this thing. And I think it would be a fascinating result. Now, the whole problem is you might get a negative result, in which case it's, what do you do? Don't blame me if that happens. But it's a question that fascinated me when I saw it.
Okay, there were some more questions.
Over here.
I think I can speak loudly enough. So in many ways, code, especially the one, thank you, code, especially the one that is already in production, has been compiled.
Yes.
So we're dealing with, I don't know, bytecode or whatnot, which means a compiler would have gotten rid of dead code, the compiler would have gotten rid of all of those things that effectively make that code more fault tolerant, right? Because it compiled under one round of assumptions, then something happens in the neighboring systems, all of a sudden preconditions fail, therefore that redundant stuff that happily got removed at compilation is what makes this software stable. Any comments?
Well, yeah, I mean, the first comment is a lot of the resilience happens not in code that is never executed, but in code that executes most of the time and just can, by chance, execute okay with the invariance violated if you do these simple things to keep the program going. So there's some inherent robustness there. Second thing is compilers aren't as good as removing dead code as we'd like. But, what are you going to do about that? The other thing, though, is that this whole business of undefined behavior gives compilers a lot more freedom than they should have. And they'll generate bogus code for them, and then you got issues. So I don't know. I mean, most of our techniques don't interact with the application. Well, no, actually they do. You can interact with the application at all the different levels, from source code, bytecode, down to some language code. Yeah.
Okay, so thank you for the talk. So I tried hard to formulate my question in a less abstract way, but I still think it's an abstract question, and I hope it makes sense to you.
Okay.
But so in one of your slides, you had a graph that on the left-hand side, like simple programs on personal computers, and we get to the right-hand side with the complicated environment and complex program. So I think, I'm not sure what is it, but I think there is a reason that we get from left-hand side to right-hand side. And I feel like if that reason is still there, it's gonna be somehow an obstacle to your research. What do you think is that reason, and do you have a plan to tackle that? Can it be prevent your research to become practical?
Okay, so I think, look, I mean, I have never aspired to do practical research. Having said that, sometimes you have to explain why your research will be practical. Everybody's familiar with this, right? So I think that, but to answer your question directly, here is the path towards practicality. So the goal of this research is to encapsulate the expertise you need to operate in these complicated environments. I think that expertise will continue to remain rare and expensive. So people will be motivated to automate away as much of that expertise as they can. And I think what we've proposed here is one way of automating that expertise. And in some sense, all these complicated APIs are an attempt, and a partially successful attempt to automate that expertise, right? If you use, Spark or Hadoop or Redis or any of these things, they're dealing with an enormous amount of complexity for you. And all I'm proposing to do here is take that up yet another level and automate it so you have to think about even fewer things to use these platforms effectively. Now, the reason that this software has to exist is because these platforms give you something that you can't get on your laptop. They give you scalability, they give you persistence, they give you fault tolerance, they give you global worldwide infrastructure. And I think there's going to be a set of issues that show up there that you have to deal with again and again and again and again. And our goal is that by encapsulating the expertise of the few people who know how to do it, we'll be able to come up with a situation that's going to be compelling enough, a solution that's going to be compelling enough for people to use, even though it's not going to be painless to use. That's what it is. But we'll see.
Yes, here.
Oh, okay.
Thank you for the talk. It sounds to me that you completely gave up on the idea of writing correct code because, well, we have these fields, as it was said before, well, we don't care, we just don't write it, we read a random value or something like that. Also about the user, well, user don't care if because they just click next. But don't you think we should be more demanding about, we should educate people to be less tolerant about a program that doesn't work? It shouldn't be that common to just refresh the page because it didn't work. We should demand more from software, and as developers, we should also demand more from the tools we can use to write correct code instead of just, well, whatever, this is software, it doesn't work anyway.
Well, I mean, look, that I think is the dominant philosophy in this field, and I don't think it's a bad philosophy. Because if you say, I just don't care, you can't accomplish anything in the world. So I think it's important that developers care. I think it's important that developers try to write good code. In practice, what the world wants is lots of functionality, and they're much less concerned about code that is flaky, periodically doesn't work, or systems that sometimes don't work. And I think people have become conditioned to that. I don't know a good way around it. And in some sense, it starts boiling down to issues about what sort of society do you have? What are your expectations? And the thing that I worry about is, if we have a society that's going to impose too many limits on, too many constraints on what you can deploy and what you can try, it's going to move slower than other societies that are more reckless. And so you're going to lose out the global competition if you don't keep up. So trying to impose regulations on systems is a risky business. On the other hand, having too few regulations is also risky as well. So I don't know how to balance that risk identically, but I think that's a key question we're going to have to face across all of society as we increasingly deploy at an ever faster rate all of technology.
Thank you.
Okay, I think we have time for just one more question.
She's been trying to ask the question for like 5 minutes. So.
Sorry. Okay.
Wait, I get the last questions, I guess. So your idea for resiliency, I can sort of kind of wrap my head around once. But actually, for dealing with a buggy program, you're actually introducing another bug by returning a wrong answer.
Oh, that's not a bug.
But no, do these things cascade, right? Is the behavior of your program, if you store that wrong answer, then some other computation is going to get, that's running correctly, is going to get a wrong answer. Does this cascade to the point where you're actually going to get chaos and your answers mean nothing?
Okay, that's a great question. And the answer is, for server programs, what you'll see is within the processing of one data unit or one network packet or one mail message, you'll see errors cascading dramatically through that code. Okay, you'll get thousands, even hundreds of thousands of these events triggering. But these programs tend to have, most programs tend to have short error propagation distances. Once you're done with that particular piece of code, it comes back around to the main event loop. If you preserve the integrity of your data structures, which this technique does, it will then go on and tend to process the next few data structures correctly. Now, the problem you're worried about here is, let's say I start putting this in my database, and then I start propagating, I have these long dependency chains throughout the database. Theoretically, that can happen. We haven't observed it in the applications we're looking at here. There tends to be enough of an interface between the program and its database so the corruption doesn't tend to be so bad. But I agree this is an issue, and you'll have to deal with it if and when it occurs. But it occurs remarkably infrequently given people's expectations.
Okay, and so we have a small gift here from the SLE conference, which is just following Gypsy. We've got we went for some local things, not local to Boston, because we're from Boston. So, well, at least we live here anyway. But local to New Zealand, so it's actually some New Zealand gin. I like gin, maybe gin and tonic.
Great, thank you. I appreciate it.
No worries.